Hey everyone, in this video we're going to predict a car's fuel efficiency measured in miles per gallon using Gradient Boosting Regressor. Our goal is simple: predict how fuel efficient a car is based on its specs, using features like horsepower, weight, acceleration, displacement and model year. The higher the MPG, the more fuel efficient the car is, and since the MPG is a continuous number, this is a regression problem. We're using the AutoMPG dataset from Seaborn's public repository. It has around 400 cars, each with features like engine size, horsepower, and origin. Our target column is MPG, which will predict, and you can see a small sample of the dataset in the current slide. Moving on, the pre-processing flow. Before training, we have to clean the data. For numeric columns, we handle the missing values using the median, and for categories like origin, we fill in the most frequent value and apply one-hot encoding so the model can handle it numerically. And finally, we split the data, 80% for training and 20% for testing. Before we begin, what is gradient boosting regressor? Think of it as a team of small decision trees. The first tree makes predictions, the next one learns from its mistakes, and each following tree keeps improving. We used a total of 300 trees, a learning rate of 0.05 and a max rate of 3, which keeps the model balanced between accuracy and overfitting. Here's the model pipeline. We can see that we first take the raw data, then pre-process it, then apply it to the model, and then we get the predictions. Moving on to the model performances, there's a graph of the predicted versus actual MPG, and after training, our model achieved a root mean square error of about 2.3, meaning it's usually off by only 2 miles per gallon. The R-square score is 0.89, which means it explains around 89% of the variation in MPG. And as I mentioned, the scatter plot shows that most predictions align closely with the actual values. Exactly what we want. Moving on to the feature importances. Weight and displacement dominate, each around 0.35, followed by model year and horsepower. This means that heavier cars and larger engines usually lower MPG, while newer models tend to be more efficient. Let's take a look at how the model learns. To understand how the model improves, we plotted how the error changes as more trees are added. For training and testing, error drops quickly, then flatten, showing that each tree keeps visiting smaller and smaller errors until the model stabilizes. Now, why predictions change? The partial dependence plots, as shown here, explain why the model behaves the way it does. As weight or horsepower go up, MPG drops. As model year increases, MPG rises. These results match new real-world logic, meaning that newer and lighter cars are simply more fuel efficient than older and heavier ones. Finally, let's take a look at the summary. So to summarize, we built a gradient boosting regressor model, cleaned and prepared our data, validated it thoroughly, and discovered the most influential car features behind fuel efficiency. Thank you, everyone.